Okay, before we look into the seismic damages, let's see why damage should at all take place. Okay, damage should at all take place if we are designing properly. That is the first question anyone can ask you. Okay, इसका लिए interview के लिए this is a very important question. People will ask you, you have designed a structure for earthquake. Why the hell the structure will have damage? पूछ तो सकता है ना? Design it properly. One of the answer is that the earthquake is an uncertain phenomenon. I have followed code, designed it. It may so happen that the earthquake which has come is some earthquake for which, or the intensity for which the code has not designed the structure. One answer is because it is uncertain. This is one answer you can give. No one can take credit. Code cannot take into account any future earthquake that will take place. Only some probable earthquake which has been observed in the past. Based on that, the code has given something. So this is one answer. But more dangerous answer is something else. That is our earthquake design philosophy. So let's look at this earthquake design philosophy. Seismic design of structure follows a code of practice which varies from country to country. Every country has a code to follow. Indian code that we have formulated has more similarities with Euro and American codes. ठीक है? So ये फिर चला गया. क्यों जा रहा है? हाँ. क्यों? Can you tell me why Euro and American code? हाँ? अरे नहीं, ऐसी कुछ बात नहीं. Our cloth has more similarities with American or European clothes. Why? नकली करने में उस्ताद है ना? उधर का सब नकली करके खाते हैं. अमेरिका ने किया, यूरोप ने किया, फिर मैं उसका नकल कॉपी मार के उसी तरह का मसाला बनाता है. That's a shame for us, or it's a shame for us, right? Why it is shame for us? Because of me and you. I don't teach you properly, and you don't want to learn it properly. इसीलिए this is the kind of thing happening सब जगह में. Anyway, and just this is joke by the way. The important thing is that the European American code, they have more information, they had investigated it more, they had more earthquakes, so they have got more data. Obviously, they are able to formulate the code in a better way, and we try to make our code similar to them, but not exactly the same. We make a difference, okay? Difference, and we have developed our code. Indian code adopts a dual design philosophy in which, in fact, most of the code follow a dual design philosophy in which structures are allowed to enter into the inelastic level earthquake and suffer extensive damages without collapse in the extreme level earthquake. Okay? So this is a very important statement. This might have been told to you also before by your teachers while teaching the earthquake design. that we say that the structure should, for earthquake design, that means जैसे कि design करते हैं, should enter into elastic range whenever there is an earthquake. That means no more remains elastic. So if it has to get into the elastic state, then there must be some damage. Okay. So some damage is allowed automatically. And for earthquake, which is severe earthquake, in that case, the structure will be severely damaged, but without collapse. Okay. So this is our design philosophy. That means in the design philosophy itself, we are accepting damages in the structure because of earthquake. So say you passed your course and you somehow go after an earthquake and visit the building, and you see that there is no cracks anywhere, no concrete has fallen down, right? Then what do you say? The structure is nicely designed or not? क्या बोलोगे? You have gone for a visit of a structure after earthquake and found that just there is no crack, even nothing has fallen down in the form of falling on anything, nothing. And the earthquake was of 6-degree magnitude. 6 magnitude. Will you call the design to be a good design or a bad design? Bolo?
Bad design.
Bad design, that's good. Bad design. Why?
Because it was not allowed to go.
Because he has not followed the code. If he had followed the code, then some damage should have taken place. All right. Now, why it is so? The reason is that, second point, earthquake is a infrequent phenomenon. हो भी सकता है, नहीं भी हो सकता है, 10 साल में हो सकता है, 20 साल में हो सकता है, right? So, if something is uncertain so much, then why should I take it into a day-to-day life design? For remember, dead load, live load is a day-to-day affair. Dead load is always there, live load is also day-to-day. But earthquake is not that. It may happen, it may not happen. So therefore, why to make the structure unnecessarily uneconomic? Okay. So therefore, the design philosophy is that will allow some damage to take place to make it economic. But damages will be such that we will be able to repair it and go ahead. There is no problem. And if there is an excessive earthquake coming, the structure may have a severe damage, but people will not die. It will not fall down. People will run away. After that, the structure may be retrofitted or may be replaced. That is different story. Okay. So this is your basic earthquake philosophy of design. So damages has to be there. Okay. Next, all of you have come across the design force, which is there for earthquake resistant design, has got a reduction factor R, importance factor R, and there is some spectral acceleration, and using that you find out an equivalent lateral load, equivalent static lateral load. Although the earthquake is a dynamic effect, but you convert it into intelligently into an equivalent static load, and with the help of that equivalent static load you design the structure. Okay. Here also two very important questions comes, which again people can ask you. So these are the questions which are not exactly common sense question, but some kind of understanding, but at the same time not very difficult. There is no mathematics and all that thing people are asking. For example, why the damage you should allow? You can answer. Because you don't want to make it uneconomic design. This is simple. Ho gaya, khatam. Similarly, if someone says that earthquake is a dynamic effect, how you are considering in the code a equivalent static load to design? Why? Why static load? Common sense question. बताओ. Common sense question is dead load is dynamic load? Live load is dynamic load? No. They are all static load. And when you design, do you design only for that dead load, only for live load, only for earthquake load? No, all the three together. You add them together. Okay? If you are adding them together to find out the member forces, then all the three should be static. Otherwise, how can you do that? Okay? So in some way you have to make it static. One of the way to make it static is that take the maximum value due to earthquake and add it. But which maximum value will take? We do not know. Because earthquake itself is an uncertain phenomenon. Okay? So therefore the codes basically come out with certain equivalent load, static load, for which you should design the structure for earthquake. And that's all about the earthquake code. First thing, it tells you how to obtain the equivalent static load. Right? So that is the reason why you are having an equivalent static load for earthquake. Answer हो गया? This answer in सब कोई भी पूछेगा तो you should be able to tell. Right. The moment you are doing this, then you will find this R factor is coming and I factor is coming. Importance factor and R factor. This also has been taught in your seismic design earthquake design courses. I factor is importance factor and R factor is a reduction factor. And there is something called SS, spectral acceleration or jet factor, with the help of which you multiply. Okay. And weight is there, W. Okay, you find out the base here. Now these are the things are done. Importance factor is that if it is school building or it is ordinary building, out of that you will give more weightage to school building, because the death will be more if it fails. Hospital building, I will be more. Individual building, सिर्फ मैं मर जाऊंगा, ठीक है ना, दफना जाऊंगा और कुछ नहीं होगा, कोई प्रॉब्लम नहीं है, बुढ़ा गया. So the important thing is that there is an importance factor. Similarly, there is a reduction factor. This reduction factor is associated with the damage. I calculate an equivalent static load for the earthquake. The question is, shall I use this equivalent static load for the design in interactive? The answer is no. Because I want the structure to go into the inelastic state. So I designed the structure for a slightly less load, so that when the actual earthquake comes, the structure will go into the inelastic state. So that is the meaning of your reduction factor, R. You divide by that reduction factor. And it depends on different structure to structure, this R factor is given. All right? So the R factor is connected to the damage that you are allowing into the structure. What damage has to be there? So you can see that whenever we are talking of any seismic design, whether it is a performance-based design or ordinary seismic design, the damage is an essential part of it. चलो सो जब wind ये क्यों ऐसे कर रहा है? ये सब तुम लोगों को पता है. I don't want to JDI/2 और VB ये सब देख लिया तुम लोग. All you have seen, you have this. So this also you know seismic design requirement that the detailing, reinforcement detailing should be proper, and there are some other code provisions which all of you have done in earthquake resistant design of structures. Okay, now let's come to the failure, which is the important thing, damages and failure. Whenever the damage takes place, okay, the damage takes place in particular way. All structures are not damaged, or all elements are not damaged in the same fashion. For example, some structures may have a shear failure. Some structure may have flexural failure, right? So mostly these are the two types of failure: shear failure and the flexural failure. They take place in the individual members, and accordingly we see that kind of crack patterns. And there are of course spalling. Okay. And because of the spalling, the reinforcement get exposed. So these are the few things of your damages, seismic damages. Now, unless we have a full damage getting into the structure does not fail. Okay. Or a structure or a joint must be converted into a mechanism. And unless that mechanism takes place or happens, but neither that joint nor that structure will fail. And why, all of you know, mechanism means one more degree of freedom over and above the what? 1 degree of freedom over and above statically determinate. It's a mouthful that I told you previously also. Difference between mechanism and statically determinate structure and indeterminate structure. Statically determinate structure, no redundancy. Okay? Statically indeterminate structure, at least one redundancy. Mechanism, one more degree of freedom than statically determinate. So that makes a mechanism, then only it fails. So the damage will be such that either a complete mechanism will take place or a partial mechanism will take place. Then only the structure fails. So mechanism is the most important thing. So what are the different types of mechanism that can take place? Let's see. Say this is the building, and I was telling you that the building will fail when there will be complete collapse. So for complete collapse, the hinges at the ends of the beam should take place, and all the hinges will take place, including the bottom. Then the structure has been converted into a mechanism. One, if you take out one hinge out of it, then it will be statically determinate. Okay. So it then, like a mechanism, it falls down. So this is the ideal mechanism. But let's take an example of a partial mechanism of failure, which usually take place. Say, in place of these hinges forming in the beam, say somehow or other the plastic hinge form here, 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 here. Here, 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 all along these. Then what will happen? This central portion of the frame goes away, tilts like that. Then the top portion will remain straight. Bottom portion also will be showing like that. And this portion goes like this. And on the top of this it will be resting. Okay. That means the scenario would be ये थोड़ा थोड़ा समझ लो, ठीक है ना? क्योंकि ये सब आदमी लोग पूछने वाला है तुमको कैसे फेल होता है, बताओ. फिर the floors are like that. बीच वाला में all hinges are found at the top and bottom. ऐसे करके सोए कर जाएगा. होगा कि नहीं होगा? Yes or no? Yes. Okay. Now, if you look at this building, the number of hinges which are formed are far less than the number of hinges required to convert into a collapse mechanism. Okay, so you should not fall down as a mechanism. But this is a partial collapse. Why? Because this portion has swayed like this. And all these portions here remaining intact. Now tell me, can this structure fail? Yes or no? How?
There will be additional moment.
Yes. So the additional moment is the original structure place was like this. And this has shifted, this portion, top portion, has shifted like this. So the weight is previously acting over here, now the weight is acting over here. So there is an additional movement, huge movement coming at the base. Okay, and the moment there will be huge movement coming at the base, you will find that all other points are also given away. So although it's a partial mechanism that has formed, but it leads to the failure of the structure. All right. So sometimes we find that there is not full all places the hinges are formed. There are places where still hinges are not formed, so the structure has not converted into a mechanism, so-called mechanism. But yet, we will find the structure has failed. So we call this the failure due to partial mechanism, formation of partial mechanism. Okay. The reason is that partial mechanism is that because of that partial mechanism, structure has displaced in a way so that it adversely affects the structure and leads to unbalanced force, brings unbalanced force in the structure, leading to a failure. Alright, and sometimes this is exhibited in the calculations also. That means in the calculation there is a way of calculating that when it fails due to this particular collapse, this collapse load factor turns out to be very less for a system which is having a partial collapse mechanism. The calculation shows. Even if you are solving the problem using computer, you will find that after certain formation of hinges, certain system, the computer stops. It cannot calculate. Okay. So it shows that at that time some kind of adverse displacement has taken place, and because of that the further calculation is not possible. All right. So the important message is that it's not necessary that a complete mechanism has to occur for failure. Failure can take place in a partial mechanism, formation of a partial mechanism, and that is a rather frequent phenomenon. Now, because of that kind of mechanism, this kind of fails. Similarly, if you look at a wall like this, when the complete diagonal cracks are formed, you will find that four segments, these four triangular segments, they separate out. Okay. And a failure takes place. So this is again a mechanism. It has given rise to a mechanism. So in all cases you will find that there is a failure because of the formation of a mechanism. And this is a shear crack. All of you know, diagonal cracks are shear cracks. Then these are the flexural cracks. These flexural cracks finally is converted to plastic hinge here. Okay. Similarly here, these cracks finally converted to a plastic hinge over here. So these will be all converted to plastic hinges. So these are different kinds of damages. Oh, I'm sorry. Again, this is a failure pattern. In the column, failing, and you can see that short column, you can have this kind of scenario. This is a shear crack, this is a flexural crack, this is a flexure come shear cracks. The important thing is all of them gives rise to one or some kind of mechanism. Okay. You can see that clearly here the plastic hinge kind of thing is forming. Okay. Here the shear crack is forming. So these are some of the pictures. You can see that the complete spalling has taken place. The steels have yielded over here. So that means this is actually idealized as a plastic hinge. This is what we mean by a plastic hinge. Okay. This is spalling, this is spalling. This is, you can see, this is the actual plastic hinge. This is the picture. What we show is as a plastic hinge in our computations. All the thing is yielded over here. This is all thing yielded over here. Here, at the bottom, we have bottom plastic hinges, which you put in the columns. You can see this is actually the scenario. So, I have talked about the seismic damages and ductility. ठीक है? Now next वाला लगाओ इसमें. So you have an idea about the damage that takes place. Now while we are talking about this damage, we put a limit to the damage. How much the rotation should take place, right? What will be the extent of damage? So whenever we put some limit to this, that is what is in the performance-based design. In the performance-based design, what we say that we allow damage, but not beyond a limit. So we limit this. So in seismic performance-based design, damage is a must. But to limit the damage within certain level that is what we want. Okay. And when we do a performance-based design, we say, well, there should be plastic hinges in the frame. But number of plastic hinges should be restricted to, say if it is a 40-story building, should be restricted to 20. So what does it mean? 20 means that if you have got 20 plastic hinges placed in the structure, then the interstory drift would be limited. If you have 60, interstory drift will be more. If you have 40, interstory drift will be less. So we are trying to have a limit on the interstory drift. All right. Or you can say that if you have got 40 plastic hinges, you will have more or less displacement than if you have 60. So therefore, the whole idea of performance-based design is to give a criteria that, well, you design the structure, but the displacement, maximum displacement should be this, maximum drift should be this, or maximum plastic hinges should be this, or the rotation in the plastic hinges should be this. These are the criteria. Okay. Based on that, you design your structure. It's clear? So that's the importance of the design or the damage. So you have talked of ductility, you have talked of damage. The last word about the damage is that when we will go to seismic review, we will see the damage in the building frames, especially when we talk of building frames. Damages are described as a permissible rotation in the plastic hinges. Why? The more rotation you allow, the more the structure will deflect. Okay. So one way of restricting or limit the displacement, and if you limit the displacement, the industrial drift also will be limited. So one best criteria for limiting the maximum story drift, maximum displacement, is to limit the rotation at the plastic hinges. Okay. So how to achieve that? How to achieve that, and how we can deal with this problem. So we'll come to the next topic of this rotation at the plastic hinges. Okay? Fine. इधर में आ गया. This, I think, I have told all these people, those who have not taken my previous course, मेरा इतना गंजा क्यों आएगा? गंजा ही दिखाई दे रहा है. So, this ductility I have already told. Now, this is those who have not attended my ASA class. For them, let's see what these plastic hinges are. You have seen in the figure that the plastic hinge, when we draw and analyze the structure, is this one. इसको क्या? इसको भी बीमारी हो गया.
स्क्रीन पे नहीं दिखता.
क्या गया?
स्क्रीन पे नहीं.
स्क्रीन पे वो ना नहीं दिखेगा.
स्क्रीन में नहीं दिखेगा. फेंक दो, इधर में दिखाई दे रहा है. This is a plastic hinge. Okay, that is what we do in the analysis. When you are doing the analysis, we draw it like this. Yes or no?
Yes, sir.
Now, actually it is not that. It is an idealization. And here basically I am trying to find out a rotation. In idealized condition I am trying to find out a rotation. Okay. But actually let's see what is happening. What is happening is this. Say let's take a ordinary fixed-ended beam, and when all of you have done this problem, plastic analysis, you put a hinge here, put a hinge here, put a hinge here, then using the work method, you find out the collapse load. Okay, that all of you have done. And rotate there. Okay. But if you look at the section here to here, this is the area. This is how the plastification has taken place. At the center, complete zone is plastified. That means all the fibers from the top to bottom, they have reached the yield. Adjacent section also has yielded adjacent. Then when it comes to this, from here onwards, you can see only a part is plastified on the top and bottom. And this goes like this until this portion. But here also something is there. At this portion, then rest of the section. Rest of the section are elastic. Okay. So these, we call these, this is a distributed plasticity for the entire range. In the center portion, full plastification gradually reduces, and then after that it becomes elastic. So this, over this entire portion, the deformation takes place. At the center as a full plastic, and adjacent section partly plastic, partly elastic. But overall deformation in this region is very high compared to the elastic portions. All right. So this is the actual scenario. And you can see that at the center, there is a lot of deformation. Now, if I want to do an actual analysis, I should solve this problem using finite element. That means in this region, I shall divide into finite elements, and using our finite element solution, find out the stresses at every point and get the actual picture. This lumping business will not go. But if I want to do that for a frame, the time that will require to analyze will be tremendous. So therefore what we do, we make an approximation. This approximation is called the lump plasticity approximation. That means we say that all the deformations, plastic deformations that have taken place, I am lumping at a particular point. Here I am lumping at a particular point. Here I am lumping at a particular point. And in between that, this I consider deformations considered to be extremely small compared to the rotation that is taking place at the plastic hinges. Or in other words, we use it to be a link. So we have a link now. Link means it becomes a mechanism. 3 hinges, 2 members, mechanism formation is there, and the structure fails under this mechanism. So that is what is known as the plastification. Okay, has taken place into the end. We do a plastic analysis of the structure. No more a plastic analysis of the structure. Is clear? Then the question is that if this is a plastic hinges, then I can find out the collapse load. All right. And if I know the collapse load, then I can correlate between the number of plastic hinges that should form and the load. Or given a load, I can find out plastic hinges. Given plastic hinges, I can calculate load. Provided we come to this particular stage. That means the hinges, plastic hinges that are formed, have formed, whether complete collapse or partial collapse. Under that condition, I can analyze a structure using the actual work method, right? Or mechanism method of analysis, all of you have done. Using that, you can find out, given one, the other quantity. Then our usual analysis that we do, that means the compatibility condition and all that kind of thing is not there. It's either a virtual work equation or simple equilibrium. All right. But that is about the part where I am relating the plastic hinge numbers with the total collapse load. The one thing remains is that there we are not bothered about how much it is rotating. We say that rotation could be anything, or in other words, it fails. But when we are coming to the design of the seismic performance-based design of structure, we are saying that infinite rotation cannot take place over there. The rotations will be certain limit, remain within certain limit. And that gives me the performance criteria. how it is possible. It is possible so long it is not collapsing. This structured beam, you can see it is collapsing. For a multi-story frame, unless there will be a sufficient number of plastic hinges, the collapse, the displacement will be such that it will not allow the structure to fail. Up to that state, in the number of plastic hinges will be there will be rotations in the plastic hinges. Let me show you this with the help of a figure so that it is clear to you. Say it starts like this, one plastic hinge form over here at some state. In other places, plastic hinge has not formed. Then the structure will displace this much. At this displacement, I have a plastic hinge like this. Okay? Will the structure fail? No. It requires some more plastic hinge, at least so that the deflection becomes more. So therefore, say there is a plastic hinge here, there is a plastic hinge here. So in this state, what will happen? For the further deflection, there will be rotations that will take place over here, rotation that will take place here, rotation that will take place over here. Because the moment it bends, it goes like this will become this here, the moment it displaces, the rotations here will take place from state to this, the moment it rotates, moves like this. So this rotation in the plastic hinge governs, the more the rotations will take place, more displacement will take place at the top. And whenever there is a more displacement, their industrial drifts also do more. Right? So you can see that one thing that is controlling the top displacement, the story drift, is this rotation of the plastic hinges. Unless the number of plastic hinges is such that it can collapse. So prior to that, the rotation in the plastic hinge is a criteria, big criteria, right? And performance-based design, seismic performance-based design, is centered around that. What you say, that you design your structure in such a way that the maximum rotation in the plastic hinges remain within 0.001 radian. Okay. Or you specify that your plastic rotation should remain in the range of 0.005. So that's how you can specify. And based on that, you make your analysis. Okay. That's a very, very difficult thing to answer. How do you do that? And in order to have that, we have brought in the seismic performance design principle. Our entire method of seismic performance design is based on this. Right? So this is the last word about the plastic rotation at the plastic hinges to denote the damage. And our performance-based design is that the damage is limited or restricted to certain level. And my challenge or your challenge is that I should design the structure in such a fashion so that the damage in the structure is restricted to this level. Damage will be there under earthquake. That is accepted. But you are restricting the damage. And prior to the designing of the structure, you specify it. Isn't it? So that's a real big challenge. And we call these the challenges of performance-based design. That is precisely the challenge. It is not that easy. So, we design a structure considering earthquake, dead load, live load, and then after designing, you analyze it and you do a particular kind of analysis called pushover analysis. Okay. And find out the rotations at the plastic hinges, and then you say that yes, my design conforms to my postulation that it will remain below this plastic rotation level. All right. If it exceeds, then we iterate. So now the softwares are there. These softwares immediately give you this idea. And we will see in the afternoon after lunch that we talk about the pushover analysis. And tomorrow in the tutorial, they will show you a pushover analysis being done on a frame and will be exhibited over here, and you will see that how the rotations changes, plastic rotation changes. Okay, everything will be shown, demonstrated. And today at the end, maybe 10-15 minutes, I will try to show you with the help of a video how the pushover analysis is done. Okay, pushover analysis is done to arrive at this. So, three things we have discussed this morning. This is the ductility, damage, plastification, plastic rotation, okay, and the failure, how the failure takes place, and what we mean by seismic performance-based design, and why the damages should be there. All right. तो अभी भूख लग गया, चलते हैं खाते हैं.